This is a video for AQA Discrete Mathematics. This is Linear Programming section 1.2, where we're looking at graphical solution using the vertex method. When we have two variables, normally going to be x and y, then we can plot these onto a graph, and once we've got the graph we can show the constraints and then look at the graph that we have to optimize our function. So to find the maximum or minimum of our objective function. We already have that idea that each constraint is a linear inequality, so therefore this can be represented by a straight line and then a region shaded out from our graph. We always shade out the unwanted region. This leaves us with a region which is blank, where our objective maximization or minimization must lie. And this region is what we refer to as the feasible region. So here's an example then that I'll work through stage by stage. So we've got several constraints here to look at. The first one is y is less than or equal to 3. Now whenever we're doing regions on graphs, then we start off by drawing the line showing the equality. So we want the line where y is equal to 3. And that's that line there. Now we want to indicate y is less than or equal to 3. So that will be the region which is below the graph. And now remember that what we do is shade out the region that we don't want. So we would shade everything which is above this line. Now when you're shading, you don't need to go wild about it, just a few lines taking out the region which is above the line that we've got drawn there to show that that's the region that we don't want. So everything below that line is going to be fine. Similarly, with x is less than or equal to 3, we would shade out a portion to the right of that. Now if y is less than or equal to 4x, if you think about that, this must be a line which is going through the origin and it's got gradient 4. So there's our line, and we want y is less than or equal to 4x. So the y value has got to be below the line. So the region that we don't want is going to be shaded above that line. Now moving on to the next one, 2x plus 5y is greater than or equal to 10. So we want to look at the equality. This type of line 2x plus 5y equals 10 is easiest done by thinking about covering up one of the variables. So if we cover up the 5y, it says 2x equals 10. So therefore this is going to cross the x-axis at x is equal to 5. Down here. It will cross the y-axis where we've got across the y-axis if we cover up the 2x, so that we have 5y is greater than or equal to 10, so 5y equals 10 is our equality, and therefore y is equal to 2, which is over here, and there's our line. Now we want the values which are above that line greater than that, so we're going to shade out everything which is below it. X plus y less than or equal to 5, so we want the line x plus y equals 5. That's going to cross each of the axes at the value 5, and we want the region which is below that, so we're going to shade out everything which is above. And finally 5x plus y greater than or equal to 5, so again this idea of covering up, cover up the y, we get 5x equals 5, so x equals 1. And then covering up the x, it says y is equal to 5. So this is going to cross x-axis at 1 and y-axis at 5. And we want greater than that line, so everything to the right of it. So there's our final piece of shading down here. So that the region that we have left is that polygon there in the center of the graph, which is what we call our feasible region. Now I've got a nice neat version of this, and there it is. So this shows us our feasible region. So just a reminder then, we always shade out the unwanted region, leaving us with the region, the feasible region, as being blank. And the other thing is that the feasible region there, we would label, normally we label it as R, just for region. Once we've drawn our graph then with these regions, we could look at optimizing some function. So for example, let's say that we wanted to maximize p equals 3x plus 4y. So in that particular case then, we would look at the feasible region, and we would say that the polygon has got 6 vertices here, and the maximizing point must be at one of the vertices. Now as this is maximizing, then the vertices must be either to the higher point of the graph or to the right. So we're going to, when you're maximizing, we're going to be moving across in this direction. So we could check this vertex here, V1, and this vertex here, V2. You can see that anything else is going to be smaller than that in terms of maximization. So V1 there we can see is at the point 2,3, and V2 is at 3,2. So if we calculate the profit or at each of those, so at V1 the profit would be equal to 3 multiplied by 2 plus 4 multiplied by 3, which is equal to 6 plus 12, 18. And at V2 we get the profit is 3 multiplied by 3 plus 4 multiplied by 2. So they've got 9 plus 8, which is 17. So our maximum profit is given by this vertex here. Now in the maximization problem, it wasn't too difficult to calculate the values of x and y at each of those vertices. However, when we're looking at minimization, then we're going to be moving left and down this time, back towards the origin to get our smallest value. We must be getting smaller x's and y's. So we'd need to check each of these vertices here. So let's look at that. Now, we can't actually read these off easily from the graph. So we'd have to do this by calculation. So if we take V1 for example, we could see that this line here is the line x equals 3, and this line is the line where we have 2x plus 5y equals 10. So the intersection is where those two equations are solved simultaneously. So we have therefore if x equals 3 and 2x plus y equals 5, 2x plus 5y equals 10, I beg your pardon, then we can substitute to see that 5y must be equal to 4, and therefore y is 0.8. So that we have at that point then the profit is equal to 3 multiplied by 3 plus 4 multiplied by 0.8, which is equal to 12.2. Now you'd need to do that sort of exercise for each of the vertices. Strictly speaking, I suppose all 6 vertices, but if we look at V2 and V3, then what I'd ask you to do is to check that when you look at V2, you actually get a profit of 8 and 21 over 23. So we'd need to solve this for V2. The profit is 8 and 21 over 23. So whether you're maximizing or minimizing, if you've got a situation where you can't be certain of the point, you can't read off the values from the graph, then you must find the intersection of the lines by solving the equation simultaneously. Well, that concludes this video on the vertex method. What I'm going to do in the next video is show another method which is referred to as the objective line method for finding maximize and minimizing points on our graph.